One way to solve this system of masses is to look at this through a lens of energy. So let's let it fall a certain distance, delta x, and we recognize this would lose potential energy and this one would gain potential energy. Where does that energy go? That energy would be translated to kinetic energy. And so we could say, yeah, the change in potential energy is equal to the negative change of kinetic energy. If you lose potential energy, you're going to gain kinetic energy. And so we can look at the potential energy we lose and convert it to kinetic energy that we gain. And we can say, sure, if we start with some kinetic energy, we would say, yeah, this is the kinetic energy that I start with, plus the extra potential energy that I start with that I lose. That turns to the final kinetic energy that I finish with. But this could fall onto a spring, compress the spring, and you'd say, oh, there's some potential energy in that spring. So this could be thought of as the energy we start with. This is the energy we finish with. So what do we need to do? Let's define an axis, and let's call this the positive x direction. And then I can find, yeah, this is the potential energy of mass 2, this is the potential energy of mass 1, and these are their kinetic energies. But the distance this one moves is going to be equal to the distance this one moves, so we can pull out the x and the g, and we just have the sum of the masses here. And these have the same speed because they're connected by a string. And so I can pull the v out and say this is just the final velocity of the system, and I can label this the mass of the system. And then you're like, oh, well, these would just cancel, and I wind up with just like I'm dropping a mass. And so you realize the mistake was, of course, this one is losing potential energy that is turning into kinetic energy. This one is sucking up some potential energy that takes away from the kinetic energy that you would be gaining. So we need to put a minus in here and recognize that I'm calling this the positive direction of the system, and that brings a negative here as well. So when we look at this, if the masses are the same, the final velocity is 0, or there's no change in velocity. If we drop out one of the masses, like let's say mass 2 is infinitely large, or mass 1 is 0, this is going to convert to just as if you drop a mass and it falls under the acceleration of gravity. And so what if we want to find out other stuff, like acceleration or forces or tensions? Well, we can say, all right, this is the final velocity of the system, and we started at v naught equals 0, right? And if you didn't start at v naught equals 0, you would just say you had extra kinetic energy that you started with, and you put it right there. But from these two, from the final velocity and the initial velocity, we can find v average, right, by averaging them. When we know the average velocity and the total distance, we can find the total amount of time it takes, because average velocity is change in distance over change in time. When we have the change in time, and we can get the change in velocity between those two, we can get the acceleration is equal to the change in velocity over the change in time. And we can get the sum of the forces on each mass, that's just equal to the mass of which body we're looking at, times the acceleration. And we know that the acceleration of this one downward is equal to the acceleration of that one upward. So let's say we want to find this tension. How do we find the tension here? Is the tension equal to the force of gravity pulling in the other direction? Well, it could be. If it was, what does that mean? It means that this system is in equilibrium. It's not accelerating. If it's accelerating in this direction, this tension must be greater than that. If it's accelerating in this direction, this tension must be less than that because it's accelerating downward. So we would say, right, the vector sum of the force about mass 1 is equal to mass 1 times the acceleration of 1. And so that would be the force of gravity plus the tension is equal to the mass times the acceleration. Then our accountant would come in and say, well, let's call this the positive direction, and then this is a negative force, and then tension is equal to m1a1 plus the force of gravity. So let's check again. If there's no acceleration, they'd be equal. If it's accelerating upward, then acceleration is positive and tension will be greater than the force of gravity. I love it. How about this tension up here? How do we find that tension? Now the body that we're going to look at is not these guys, but this body. And we say, oh, that body, it has 2 strings pulling down on it. How many strings pulling up? Is it accelerating? It's not accelerating, it's there motionless. So this tension pulling up has to equal the sum of these two tensions pulling down, because those are the forces acting on it. Unless it has mass, but it's massless. So we would say the vector sum of the forces on the wheel, we'd say the vector sum of the forces on the wheel is equal to the mass of the wheel times the acceleration of the wheel. If this is 0, because it's in equilibrium, we would just say tension wheel plus tension 1 plus tension 2 is equal to 0. And your accountant comes in and says this is positive and these two are negative. So we can see the tension in the wheel is equal to the sum of these two. And if these are the same, then the tension in the wheel is equal to 2 times the tension on either string.